In this video, we're going to be taking a look at enzymes. This is part one of two parts of enzyme videos. So first and foremost, we have to define what is an enzyme. Well, an enzyme is a substance that is created by a living organism that acts as a catalyst, which means that it speeds up reactions. Most commonly, they are proteins. That's why it says usually. So it's proteins that are created by an organism to speed up a reaction. We recognize them in terms of chemical names because most often they have the ending ase, lactase. You'll see that and learn to recognize that as an enzyme. So how do they speed it up? They speed up a chemical reaction by lowering what is known as the activation energy, or the energy required to be inputted before a reaction can continue. So for example, if we have a non-enzyme catalyzed reaction here, notice the energy barrier that these frogs have to go over. If there is an enzyme catalyzed reaction, the barrier that the frogs have to go over, the reactants have to surpass before becoming products, is significantly lower. So let's take a look at some real life examples. Without an enzyme, we take a look at the lactose, which is a disaccharide. In order to become monosaccharides, that bond has to be broken. Well, in order to break that bond, there has to be an input of energy. That bond has to be destabilized so that it will break. So that is the activation energy, the energy that has to be put in to break that bond. Afterwards, there is a release of energy. However, if it is enzyme catalyzed, you'll see this green molecule here is the enzyme. Lactose will bind to the enzyme lactase, and that enzyme, you can see, actually changes the shape of that bond, and it destabilizes that bond so that less energy is actually required to break the bond. Again, once it's hit that activation energy, there is a net release of energy because there's less energy, because there was energy stored in that bond that is released upon its being broken. So this leads us to an enzyme energy profile. So what we want to take a look at is up the y-axis, we have the amount of energy or free energy in the system, and then we have the progression along the x-axis. So we have a red and a blue reaction line here. When we take a look at this black reaction line, we have our reactants up here, what we're starting with, and our products, the molecules that we end up with. The course of the reaction without reactants requires a significant increase or input of energy before that reaction can progress to produce the products. So this is the EA, or activation energy, without the enzyme, going from the reactants to the top of that peak. However, when it is enzyme catalyzed, you notice that that peak or that activation energy is significantly lower. There is still an input of energy required, but it is less than when you did not have the enzyme. Key thing to notice is that the reactants start with the same amount of energy because you're starting with the same reactants, and the products end with the same amount of energy because even though it's enzyme catalyzed, you end up with the exact same products. So the delta G, which represents Gibbs free energy, or the amount of energy in the system, is unaffected. The energy between the starting reactants and the products is the same whether you have used an enzyme or not. So we call this type of energy an exergonic reaction. Exer meaning to exit or the release of, gonic, energy. So if we look at the difference between a reactant to a product, there is less energy left in our products than was in our reactant. So there was a release of energy, a net release. This is a common energy profile for catabolic reactions, when we're going from a large molecule and breaking it down into smaller subunits. Sometimes this will be called an exothermic if it is a release of temperature or of heat when the reaction progresses. Common examples are cellular respiration or combustion. Now, we also have to take a look at an energy profile when there is a net input of energy. So noticing our reactants are starting with a low amount of energy, but our products end with a higher amount of energy. So the black line, again, is a course of reaction without the energy. Notice a much higher activation energy than when we have it enzyme catalyzed. So noticing the activation energy much lower with the enzyme being present. Again, the total change in energy is the same whether you have an enzyme or whether you do not. So this is called an endergonic reaction because you have had an input of energy of some sort. This is true of anabolic reactions because it takes energy. Say you have two monomers and you want to join them together. It takes energy to create that bond to hold them together. Often referred to as an endothermic if the input of energy is in the form of heat. So this is common in photosynthesis, absorbing the heat energy or solar energy from the sun and storing it in glucose. Also true in melting of water. So enzymes use several different strategies to decrease this activation energy, and we can use the acronym MODS squad. So this will help you remember the ways that they can do that. So M is for creating a microenvironment. So if this blue entity over here is our enzyme, they can create a little microenvironment that maybe has a different pH, or maybe has a different charge, or maybe is hydrophilic or hydrophobic, that will either attract the substrate or will allow the bonds to be broken or created more readily. O means orientation. This enzyme can hold the substrate in a particular way such that it will meet up with something else, or it will cause it to break its bond more easily. So holds it in the proper orientation or direction for the reaction to progress. D, direct participation. So the enzyme actually is participating in that reaction. It's not just kind of a passive bystander holding that substrate or that molecule in place while the reaction occurs. And lastly, straining bonds. That enzyme can actually kind of bend a molecule such that that bond is weakened enough that it could break, or bend it so that it is able to bond with another molecule. So MODS, or the MOD squad, are the strategies that enzymes can use to decrease activation energy, or the energy required for a reaction to progress. So why are enzymes so important? Why does our body require enzymes to function? Well, if you think of the particle theory, heat is usually what is used to speed up reactions, right? The more heat, the faster the particles move, the more likely they are to bump into one another, the more likely the reaction is to progress. However, as we learned when we talked about macromolecules and proteins, proteins will denature and will lose their shape at high temperatures. Well, as soon as they lose their shape, they lose their function. So heating up the body is not a very good way to speed up those reactions. And we couldn't heat our body up enough without doing enough damage. So we go to enzymes. So our body can't rely on those increased temperatures because we would do too much damage to too many other enzymes and too many other reactions. So why is it enzymes that our body uses? Well, they're not consumed during a reaction, so this saves a significant amount of energy. Our body doesn't have to keep reproducing them every single time a reaction has occurred. So an enzyme will be a part in speeding up that reaction, but the products will continue on. That enzyme can be recycled and reused. The other reason our body relies on enzymes is they exhibit substrate specificity, meaning that this substrate of the molecule that is binding to the enzyme fits with a specific shape. All enzymes can't be used for everything. They are used for one particular reaction. So how is it that they do that? And this fitting a substrate to an enzyme is called the lock and key model. Noticing that enzymes are specific to their substrate. So there's one substrate or one molecule that will fit in the active site of an enzyme. So for lactase, lactose is the only molecule that will fit into the active site of that enzyme. Other molecules will be floating around inside the cell, not affected at all by the enzyme lactase being there. Now, once the substrate has bound to the active site of an enzyme, so if we look at the enzyme here, here's its active site, the substrate binds to it, we end up with what is called the enzyme substrate complex, just meaning that they have bound together and the beginning of the catalyzed reaction has started. There's also what is known as the induced fit model, in that this enzyme here, once the substrate binds, will slightly change its shape to keep hold on that substrate. So the active site undergoes some sort of a conformational change that will better accommodate that substrate, either by straining the bonds or holding it in a particular place. But if you notice here, it actually changed its shape a little bit to kind of help that reaction progress.